Hello, hi friends. In our previous lecture, we have completed up to the 55 number question in the continuation of that lecture series, that is SSB lecturer Physics Solution 2023. In this lecture, this is our 12th lecture, and we are starting from 56 number question. The 56 number question is an anharmonic one dimensional oscillator has the Hamiltonian. This is the Hamiltonian is given. This is the Hamiltonian. And also the on part of the wave function is also mentioned here. That means we don't have to assume the wave function in our mind. Okay, it is already mentioned. We don't have to assume. Okay, so what you have to find? We have to find the ground state first order correction in the energy. So how can we find? Just apply the perturbation theory. Okay, so let's see the solution. This is the perturbation formula, that ground state. Okay, if you see a x to the power 4 is the perturbation. Okay, and this a is constant, so take it common out from this term. Okay, from this operation. So a naught is here, and the formula of x to the power 4 is 6n square plus 6n plus 3 s square by 4 m square omega square. Okay, this is a formula as you see in this, in the right side, in my right side. This is the formula. Okay, now as it is mentioned that we have to find the correction in the ground state. So for ground state n equal to 0. Okay, as we are dealing with the harmonic oscillator, whether it is anharmonic or harmonic, that doesn't matter. But for harmonic type of system, the ground state starts from n equal to 0. Okay, and the fast acceleration state is n equal to 1. But in case of hydrogen like system, the ground state starts from n equal to 1, or you can say for infinite potential well also. Okay, so you put the n equal to 0 here, and you get 3a s square 4m square omega square. But if you see the solution, there is no such type of term. Okay, so what you have to do, we have to convert it in another form. Okay, so just put the value of omega square, and omega square is this, put, and you calculate, some term will be cancel out, then you will ultimately get this option. Okay, and you just find out which option is correctly matching with this answer. Now coming to 57 hour question, the 57 hour question has asked in case of a Stark effect, if E vector is the applied electric field, the shift in the energy in the first order, in the first actual state of the hydrogen atom is proportional to what? That means we have to find the proportionality of a shift in the energy with the which term of external electric field. Does it proportional, linearly proportional, or it is proportional to e to the power square or any power term? So we have to find that. Okay, and remember, here it is mentioned that, explicitly mentioned that we have to find the first order in fast acceleration state. Okay, in hydrogen atom, for fast acceleration state, that means the ground state is, for hydrogen atom, the ground state starts from n equal to 1. For fast acceleration state, okay, it starts from fast acceleration state means n equal to 2. Okay, so now you just see, for n equal to 1, that means for n equal to for the ground state. Okay, if you see the ground state wave function of a hydrogen atom is psi 100, where this n equal to 1 and l equal to 0 and ml equal to 0. Okay, so this is the term, and if you calculate this and this is the perturbation, s dash is the perturbation. That means when you place a hydrogen atom in any external electric field, this is the perturbation. This much is the perturbation. Here this z cap is not suggesting any direction in the z cap direction. It simply says that this is the operator, this is the position operator along the z cap, along the z direction. Okay, so, and this E is the charge of electron, and E naught is the external electric field that we have applied. Okay, so these two term will can be taken out, because these are constant. So you just put the value of r operator, z operator, that is nothing but r cos theta, this r cos theta means we are taking in spherical polar coordinate system. Okay, so in spherical polar coordinate system, the z vector, sorry, the z operator has this value r cos theta. Okay, so now if you do the calculation for this integration, this is a integration, and this is not this is a complex integration. This is not a complex integration. You just do with the there will be a differential small infinitesimal small volume element. Okay, so in that volume element, that is the r square sine theta d dr d theta d phi. Okay, so in that volume term, if you see that there is a sine term here. Okay, sine theta. So when sine theta will multiply with cos theta, then it will, we can convert it into sine 2 theta. Okay, so if you integrate that sine 2 theta, it will eventually give you 0. So ultimately the whole term will be multiplied with 0, and it will be 0. So that's why we get E ground state equal to 0. That means if you place any hydrogen atom in any external electric field, there will be no splitting of that label for that ground state. Okay, this that means this. Okay, the physical significance of E ground state, that correction, first order correction is equal to 0 means the ground state does not split. Okay, now if you see the first excited state, that is n equal to 2. For n equal to 2, we will get fourfold degenerate state. What does mean by degenerate state? Degenerate state means such type of state which are different in appearance. That means the state are have different equations. Okay, or different wave functions, but they correspond to the same eigenvalue, or we can say the energy. That means all four states have same energy. Okay, for example, in case of n equal to 2, 2p, 2px, 2py, and 2pz, both these four states have same energy. What is the energy? 3.4 electron volt minus 3.4 electron volt, for example of a hydrogen atom. Okay, so these four pole degenerate state have same energy like this, but the states are different. Like such type of states are known as degenerate state. Okay, so for degenerate state, we have to apply the degenerate perturbation theory. And for degenerate perturbation theory, these are the four states. Okay, these are the four states. Now we have to apply the degenerate perturbation theory, and in the degenerate perturbation theory, we have to find the double matrix. Okay, and if you, as there are four degenerate states, so this double matrix will contain 16 element. Okay, 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 so this is the double matrix. Now what you have to find in the further step? We have to find the eigen values. So if you find the eigenvalue, you will get 0 0 minus 3 a naught e external, and a positive 3 a naught e external. Here this a naught is the Bohr radius, and the e external is the external electric field that we have applied, and e small e is the charge of electron. Okay, now if you see that this lambda 0 0 means there are two states which do not split. That means they coincide with that initial state. The initial state has energy minus 3.4 electron volt, and as this lambda equal to 0 0 means there are two states among the four degenerate state. There are two states whose energy level does not split. Okay, and they coincide with that initial state. Okay, that means this level contains two wave functions of that hydrogen atom. Okay, in the n equal to 2 state. Okay, but there are other two states whose level has splitted. One has gone up and one has gone down. Okay, but we don't care all this type of information. We just need the information about the proportionality. and the correction proportionality, correction in the energy is this. Okay, you just take this term, and if you shift, if you see that the shift in energy is 3a naught E external, and it is explicitly you can see that this del is proportional to E. Okay, so option C is the correct one. Okay, option C is the correct one for 57 number question. Now coming to 58 number question, it has given that for a normal Zeeman effect, the shift in the energy for the nth state computed to the first order is proportional to which term? Okay, now this is also a easy question. One thing I have to mention here that you see uh, this the degeneracy here in this case the degeneracy has not lifted fully. It is lifted partially because still there are two states whose uh, energy levels are not splitted. They are considered with that initial state. Okay, so degeneracy is partially lifted here. Okay, okay, so come to the solution of 58 number question. So before doing that we have to know what is Zeeman splitting. Okay, if you see that when we place an atom in a weak magnetic field, not in a strong magnetic field, if you place a if you place an atom in the strong magnetic field, then it will be anomalous effect. Okay, so what happens is that when you place an atom in the weak magnetic field, the orbit term again split into several terms. Okay, as you know that spin orbit coupling splitting is due to the interaction of the internal magnetic field and the magnetic moment of that electron. Okay, that's why this spin orbit coupling takes place. But after those type of interaction, spin orbit interaction, if you place in the atom in an external magnetic field, spin orbit coupling is due to internal magnetic field. But if you place that system in a weak magnetic external field, then Zeeman splitting will take place. Okay, Zeeman splitting will take place. This is due to the interaction between the magnetic moment, due to the orbital angular momentum, and the external magnetic field. Okay, you see this is external magnetic field, not internal. Internal is due to spin orbit coupling. Okay, now then what is the uh, interaction energy? Del E equal to minus mu L dot B, and mu L B cos theta if you apply the dot product. Now we can write the ml cos theta as a mu L Z. That means the magnetic moment, angular magnetic moment in the z direction, and this value of this mu L Z is E by 2m ml s cut. Okay, so it is explicitly you can see that this is proportional to ml. Okay, this is proportional to ml. Okay, so what is the value of ml for a electronic system? What is this? What is the value of ml? Okay, you can it depends on L. If the value of L is 1, then ml can have 3 value. It can have a 1, 0 or minus 1. So depending on that you can calculate. So it is proportional to ml. So now let's see the 59 number question. It is given that if a particle in a one-dimensional infinite potential well of width A is subjected to the perturbation, S dash is equal to capital AX, and its the unperturbed wave function is this. Okay, then the energy correction in the nth state. Okay, okay. If you see, this is the perturbation, and this is the unperturbed wave function. Okay, we have to find the energy correction in the nth state. You just apply the perturbation formula. This is the perturbation energy formula in the nth state. Okay, this is the nth state. Now if you see specifically, if you see the question again, in the question there is no mention of whether this one-dimensional potential well is symmetric or asymmetric. So as there is no mention, we have to assume that it is an asymmetric one-dimensional infinite potential well. Okay, by default, we have to take. Okay, so and also we know that uh, for any asymmetric potential wave function or potential well, the average position of a particle is always a by 2. That means whether the whatever the length of that well, the position average position will be a by 2, or that length by 2. If the length is let's suppose L, then the average length will be average position of that particle is L by 2. Okay, but in case of a symmetric, let's suppose that well is symmetric well, then in that case we have to manually calculate those value, that average value. Okay, but as it is not mentioned any case, so we have to take that it is a asymmetric well by default. Okay, so you put a by 2 here, that means the value of this term will be a by 2, means small a by 2. Here this a, capital A is the strength of that perturbation. Okay, capital A is the strength of that perturbation, and you will get a capital A small a by 2. Okay, now coming to the last question in this video, that is, in case of fast excited state of a hydrogen atom, the first order correction, first order spin orbit interaction energy correction, EES. Okay, this is not EES, this is ELS. That means correction in due to spin orbit. Okay, now we have to find the whether the correction is shifted, that means split is has gone upward or downward. If the split is has gone upward, that means it is positive. If the splitting has gone downward, that means it is negative. Okay, so if you see the solution, the spin orbit coupling, the energy correction is this is the formula. But you remember that this formula is only applicable for L greater than 0. That means in case of S, for S orbital, the value of L is 0. For p orbital, the value of L equal to 1. Hence, for S orbital, the value of L equal to 0. That means it does not split in spin orbit coupling, because when L equal to 0, the corresponding internal magnetic field will be 0, because the magnetic field formula is BL. This is the internal magnetic field is 1 by 2 ZE mu naught by 4 pi R Q ME. Here ME is the mass of electron, Z is the atomic number of that atom. Okay, and R is the distance of that electron from the nucleus. Okay, now if you put L equal to 0, this BL, the value of BL is 0. If BL is 0, then the interaction energy, that is minus mu dot B, will be 0. That means the S orbital does not split. Okay, the S orbital does not split. Okay, this is not, the S orbital does not split. That means 2s 1 by 2 does not split. It will remain unsplitted. But for 2p 3 by 2, for 2p 3 by 2, L equal to 1, because it is p, it is for p orbital, and j equal to 3 by 2. Okay, this lower term is j, and if you put the value of this in this formula, and you calculate specifically this term, if you calculate this term, you will get positive 1. Okay, because it does not depend on this, it is always positive, this term is always positive, you get a positive 1. That means it is positive. That means 2p 3 by 2 shift upward. Okay, it is positive, but we don't know exactly, we can't find whether 2s 1 by 2 splitted moves down or moves up. Okay, we can answer this question whether this 2p 2s gone up or down with the help of a fine structure splitting and with the help of a lamp shift. Okay, then we can answer this question. Okay, we can answer the we can answer the shift of for 2p 3 by 2, but we cannot answer the shift for 2s 1 by 2. Why? Because here s orbital is present. For s orbital l equal to 0. Okay, and for l equal to 0 we cannot apply this formula. Which formula? This formula we cannot apply, because this formula is applicable only for l greater than 0. That means l can be 1, l can be 2, l can be 3, like this. Okay, so what we have to do, we have to consider lamp shift along with the fine structure splitting. Okay, so if you see that for n equal to 2, there are two l value. L can be 0, l can be 1, and s equal to half per electron. And if you find the term symbol for l equal to 0, the term symbol equal to 2s 1 by 2, and for l equal to 1 there are two term value, that is 2p 3 by 2 and 2p half. Okay, now you see this is the actual diagram. Okay, and in the diagram if you see that this 2s 1 by 2 is placed above the 2 p 1 by 2. Okay, that means what? That means the 2s 1 by 2 label is shifted upward along with this p 3 by 2. That means both of the two label, which are the label, this these two label. Okay, p 3 by 2 and s 1 by 2 has positive shift. That means the option number D is the correct one. That is is positive for 2s half and 2p 3 by 2. Okay, but you remember that this question cannot be answered only by considering the spin orbital interaction. To answer this question, we have to take into account the fine structure splitting along with the lamp shift. And you also notice that the fine structure splitting is nothing but the addition of two interactions, that is spin orbital interaction and quantum mechanical relativity correction. Okay, so by considering these two effects or interaction, we can answer this question. So I think this question has should be given grace mark, but that was not happened actually. SSB has given the answer option D as the right answer, and I think also there may be any there was no I think there was no objection for this question at the time of objection. No student I think had objected this question for a grace mark. That's why I think SSB had not given any grace mark or considered this question as a valid question. Okay, that means there is no data insufficient. So I think you got the answer. Thank you.